Okay, so let's start. I assume that you can hear me back there. Can you hear me? Okay. So a few comments, and by the way, you probably noticed that I'm starting at 12:32 because I want to give all of you time to come, and I always start with some administrative things. So I found that several of you ask me the same question that I'm starting the class with, or answer to the same question. So please either listen or ask questions if it's not clear, or come a minute earlier so you won't miss these administrative comments. So a couple of things. So I think that registration is all done. I know that a few of you that got messages from the academic office did not register, which caused you some problems with Compass. If you're still in that situation, please do it as soon as possible. So everyone will be on Compass and will be able to submit homeworks and do the exercises. I think there are just maybe 3 or 4 students in that situation. Homework 1, most of you submitted it. According to the gap between number of submissions and people that are registered, are maybe 20 like this. Either you are waiting until you are using your 96 hours, which are going to end on Friday night, or you just drop the class and maybe you're not here, in which case just drop the class. As I said, the solutions are going to be available once the 96 hours are done, because the assumption is that we're not going to get any more after that. We are still insisting on LaTeX, and if you haven't made the effort to study this, the little effort to study it, you should do it, because this is going to be the standard through all the problem sets. Homework 2 is already available, and it's going to be due next Thursday. I want to talk a little bit about it today, just to make sure that everything is clear. Really, the structure is very simple. And as of this week, we're going to try to give once every couple of weeks an online exercise. The idea is for you to think a little bit about stuff that we're going to talk about in class. How many of you have done the first exercise? Okay, almost all. So as I said, it's going to give you, each exercise is going to give you 1% extra credit. People ask question about what does it mean. Here is what it means. Let's assume, so each component in the class, I'm talking now, so if you have questions, ask me. Thanks. If you remember, there's a breakdown of problem sets, midterm, and final. Altogether, they sum to 100. If it so happens that you get 89% of this, and you did 3 exercises, you get 92. And this is where the curve starts. So it could be helpful. Yeah. Right. As I said, I don't know, as I said in the class, the due date is before class. And it was supposed to end at noon today. And hopefully it ended at noon today. Yes? PM instead of AM? Sorry about it. Okay. So that was a confusing thing. You were thinking that you'll have time to do it after class today? Okay. we'll open it until 12 p.m. because of this confusion. But next time, the principle is that I want you to do it before class, not after class. And I thought I mentioned that in class, but anyhow, I'm sorry about the confusion. So we'll open it until midnight. Yeah. I couldn't hear you. Yeah, so the reason we opened it that time is because I didn't want to open it before the homework was due, because I was thinking that, too much overload on the students. We can do it earlier. So we'll try to do it earlier if you think this is important. So that was the motivation. It really just takes 10 minutes to do. So if we give you, I don't know what, 36 hours should be enough. But we can try to do it earlier. Other questions on that? Okay, so I want to talk about problem set 2. Just to make sure that you all understand, first of all, that you have to start working on it. 2, that it's really very simple conceptually. So here's the problem. So the goal is to help you learn and understand decision trees, mostly the first problem, which is relatively straightforward, I think. And then to help you understand the notion, some important notions in machine learning, such as the expressivity of models that you learn and the impact of that on performance, and the notion of features, generating features, and so on. So there's one component that I call here RM, for reporting module, that you're going to prepare and then use 5 times or so. Basically, given a data set, you will train a model, you will run 5-fold cross-validation using this model on the training data to get a number. And then you will evaluate your model on a set-aside test set that we gave you and submit the predictions on this test. So this is kind of a module that will repeat itself. And then what you're going to do is you're going to do several tasks. Most are simple. Some will require some programming using this. So the first thing, we're giving you data which is similar in principle to the badges data that we started the class with, list of names. Some of them are positive, some of them are negative. We actually converted the data for you to features using the features that are mentioned there. So we did the feature extraction, and what you get is, I think, 2,000 examples. Each one of them is a bit vector, is a vector of 270 features. That's the data. Now, you can augment the data with additional features if you want. You're welcome to do it, but you can just stick with this data set. So that's the basic data set. With this, you're going to do the following thing. So A is done. First of all, you're going to program your own SGD algorithm, stochastic gradient descent algorithm, and you will run this evaluation module on it. As you will see, it's mentioned there, you can use any programming language you want. We gave you a skeleton for a Java program for this. You don't have to use it. You can do whatever you want. The data is given. You just have to make sure that you know how to use the data in whatever language you choose to use. B. C, you're going to use Weka. Weka is a library of machine learning algorithms. We didn't want to spend your time programming decision trees. So you're going to use this library. You'll use the ID3 algorithm from there. And you will basically, again, do the same thing. Take the data that we've prepared, learn decision tree using ID3. D, you're going to do exactly the same, only that now you're going to limit the depth of the decision tree either to 4 or to 8. Again, once you look at Weka, you'll see that there's a flag there, and it's easy to do. So you'll run, you'll generate 2 other decision trees, and again, you'll run the reporting module and evaluate it. E is the most interesting part. Here is what, and this is also where you have to do a little bit of programming, not a lot, because you already did something in B. C and D essentially require no programming. You basically just have to use the function from the library. You can use it programmatically if you use Java, but you don't have to use it programmatically. Here, what we want you is to use the decision, what we call decision stubs, the small decision trees that you learned here as features. In order to do it, you're going to generate 100 decision trees of size of depth 4. Of course, you have to think about how to generate 100 different decision trees, and we suggest a way to do it, because if you just run it on the data that we supplied, you'll get the same one every time. So we suggest to sample from the training data in a specific way. Do it 100 times. Every time, use what you did in D to learn a decision tree. Once you have these 100 decision tree, you can take the training data that we gave you, the 2,000 examples of dimensionality 270, run each one of your 100 hypotheses on it. You'll get a bit, positive or negative, and you'll form a 100-dimensional feature vector with this bit. So basically, every example that we gave you is now being converted to a 100-dimensional feature vector, where the ith bit in this 100-dimensional vector is the output of your ith decision tree of depth 4. Okay? Now you have a new data set. You started with this data set. Now you have a new data set, which is 2,000 times 100. And you run B on this data set. So you run the stochastic gradient descent on this data set. So the resulting thing in E is that you have more expressive features, not those features that we started with, but rather decision tree, small decision tree-like features. And you run stochastic gradient descent to get a linear model over these decision trees. Okay? So overall, you have one model in B, one model in C, 2 models in D, and another model in E, which is 1, 2, 3, 4, 5 models. And at the end, we want you to compare them, see how they perform on the data, and do some statistical significance using a routine that, or using the procedure that we suggest. By the way, if some of the notions, cross-validation or t-test, are not clear, at the end of the lecture notes on decision trees, I included some notes on that, which I didn't cover in class, but it's there. You can go and look at it. Questions? No questions. Completely clear? Anyone looked at it already? Yeah.
So there's another step
This is E1 here. Generate a 100-dimensional data set. Each dimension is the prediction of the decision tree. That's the step.
And then the next step is to do
Right, and then you do B, and B is run but you don't need to program it again. You just use what you've done in B. In B, you ran it on 270-dimensional data. Now you're running it on 100-dimensional data. Same thing, right? So you don't need to reprogram your linear classifier here. Yeah. Behind?
What? Behind doing this learning something.
So the idea is that, if you remember, we talked several times about linear separability and data that is not linearly separable. Right? So let's assume your data is linearly separable here. In this case, when you run your stochastic gradient descent here, you're expected to perfectly separate the data. You get 100%. Everything is going to be fine. If the data is not linearly separable, the stochastic gradient descent will not give you good results or perfect results. And the question is, what do we do now? We can either learn a more expressive classifier, which you're going to try in C and D, or you can change your feature. So this is scheme 1, learn a more expressive classifier. Scheme 2, change the features to be more expressive, which is, we showed it in several slides, and I'm going to remind you what was the picture that I had, this picture. This picture basically is kind of a cartoon that indicates my data is too expressive for a linear classifier. What I can do is I can change the dimensionality. I basically change the features, and each feature now is going to be a function, a simple function of the original features. Now, if I learn a linear function on top of it, better chances that it will be good. And that's what you're doing in E, right? So you learn the small decision trees. These are simple functions on the features. They could say x1, if x1 is 1 and x2 is 0 and x3 is 1, then say 1. Right? So it's some condition on multiple features. With these new features, hopefully the SGD is going to perform better. Okay, so if you think about it, hopefully you will develop some expectation on the relation between what you should see in terms of performance for the different sections here. Hopefully this will happen, but we'll see. But that's the idea. The idea is really to have you play with exactly the issues that we talked about in terms of expressivity, and also give you some idea on feature extraction. And finally, this algorithm that you're using in E is actually an important algorithm. It's being used in practice. We will see a little bit later, in a couple of weeks, another way of learning a linear function over these small trees. But this is almost as good as what we'll see in a few weeks. And you already have the tools for it. Other questions? Yeah. You can write a small script if you want. The idea is that you'll have to understand the notion of information gain in order to do it. So the data is really simple. If you look at it carefully, you'll see that it's even simpler than it looks. So it's easy, but you'll have to know how to compute information gain to do it. I didn't talk about 1 because I think that 1 is relatively straightforward. 2 is the one that, there are many steps. Hopefully, even though the text is long, it's well written and clear. And just to bring this point home, I kind of wrote it in a simpler way on one slide. That's the key, what you have to do. Okay, so let's move on. And so what did we say last time? We talked about 2 algorithms. I'm going to put everything here. Or if, in fact, these are really 2 families of algorithms. We talked about what I called additive algorithms. Perceptron was the representative, where basically you update weights. It's a mistake-driven algorithm that updates weights additively by essentially adding the example or subtracting the example. And we talked about, we know that in terms of the structure, it's a very, very similar structure algorithm, mistake-driven algorithm. only that the way you update the weights is you multiply the weights by something rather than add something to it. So I want to start by talking a little bit about extensions, because these sort of basic vanilla algorithms are good and interesting, and we can prove properties. We proved interesting properties for these two, but these are not the algorithms that you want to run in practice. You want to add some bells and whistles. So there are several types of extensions. The key one that are really necessary for these algorithms to perform well are related to regularization. Sort of essentially in the context of linear separators or in general, they make sure that you don't learn something, that you don't overfeed the data. Another type of extension that is often important is converting the output to probability distribution. It's a very simple thing. It also may require some tuning of a parameter here. You can put it 1, but you can tune a parameter. There's a question of how exactly to tune it that I'm not going to address now. And there are a few other extensions. Extension to multi-class classification that we're going to talk about, and some issues that have to do with efficiency, how to actually program these algorithms so that it's going to be OK. So I want to talk about a couple of the really important extensions that you have to do. And I started at the end of last time to talk about this. Basically, I talked about average perceptron. Average perceptron is a version of perceptron that is motivated by the need to actually get performance guarantees that are somewhat different than what we talked about. We talked about mistake bound. We said, OK, this algorithm is going to stop making mistakes at some point, or is going to not making too many mistakes in the inseparable case. We bounded the number of mistakes. At least I quoted the theorem. I didn't prove the inseparable case. But really, that's not what we want. And to give an example to illustrate what I mean, let's imagine the following scenario. You have 10 minutes to run your algorithm on your data. You can cycle through as many times as you want, but you're limited in time. You look at the hypothesis that your algorithm produces over time, and you see, OK, here is a hypothesis. And after a few examples, we made a mistake. We changed the hypothesis. After a few more examples, we made a mistake. We changed the hypothesis. At time 9:58, you look at your data and you see, oh, this is a hypothesis that I have now. I wonder if this is going to be the final hypothesis. But no, in the last minute, the last second, you make a mistake, and the hypothesis is updated again, and you're done. Now the question is, you have a final hypothesis. Is this the hypothesis that you want to use and take home with you to do predictions on your test data? This is the final hypothesis that your perceptron produced. But it's not the only hypothesis that perceptron entertain over time, right? Because as you were looking at what's happening, you've seen a lot of other hypotheses that were there over time. You want to take the one that you ended up with after 10 minutes. Yeah? So the suggestion here, you want to take the one that was most successful in terms of longest stretch of no mistakes. So notice that the one before, the one that you had at 9:58, was there for some time. And then just in the last second, you made a mistake and updated it. Who said that this current one is better than the previous one? Maybe not, right? Because it's a little bit different, but there's no proof. It does not come with any certificate of I'm better, modulo I corrected something on this last mistake. And the previous one maybe was alive for a long time and could be better. So the key issue here is that the intuition, and we're going to quantify this intuition, is that if you have been consistent with a lot more examples, you're probably better. So we will quantify it and show that you could actually come up with a function that says, if I'm consistent with m examples, my performance in the future is going to be a function of this m, an increasing function of this m. Right? That's what you want. And if a function of a few other things. But that's the right intuition. With this intuition, everyone agrees that this is a good intuition to have? Okay, so first of all, I'm waving my hands here. I don't know how to prove that the 958 hypothesis is better than the 959. I'm just trying to give the intuition that if you had an hypothesis that was good for a lot of examples, it's probably better under some probabilistic setting that I've not defined yet properly. It's probably better than a hypothesis that was not consistent on a lot of data. Under the assumption that everything is the same, I always sample examples from the same distribution. It makes sense that this is true. As I said, we will quantify it in a couple of weeks. At this point, I just want to sell you this intuition as a way to what I'm saying now. And what I'm saying now is that you can actually quantify it, and you can take my mistake-bound algorithm and convert it in a rigorous way to something on which I can prove that with high probability, the error rate of the resulting function is going to be low on the new coming example. Yeah? Good question. So the intuition that you had was, or the hope that you had was that the hypothesis at time t+1, after you corrected on a mistake, is going to be better than the one before. And that's a nice thing to hope for, but it's not going to happen. Right? In fact, even more, let's ask the following question. I made a mistake on this example X, and I corrected my hypothesis. What will the performance of the new hypothesis be on example X? Will it predict on it correctly? Who says yes? Who says no? Why yes? This is perceptron. Okay? So I'm adding 1 to Wi. Basically, I'm shifting a little bit the weight vector. Is there a guarantee that the example will now, that I'll make the right prediction on this example now? There's no guarantee. I'll show you a picture in a second because I was going to talk about this point a little bit later. There's no guarantee. I know that the previous one made a mistake on it. I know that the new one was corrected in the right direction. I don't know that it's not going to make the same mistake. All right? Think about it. No guarantee. Now, but in general, we want to assume that it's better, it's closer to the true hypothesis, and it's true in a statistical way, but I don't know how to prove, and in fact, it's impossible to prove something like the probability of me making a mistake on this next example is bounded by something. On the other hand, on this algorithm, which I'm suggesting here, there is a guarantee. I'm not going to prove it, but I'm going to give the algorithm. And when we get to study this model, PET, probably approximately correct, it will be a little bit clearer how to prove this thing. But let me just give the algorithm and then go back to the question. So basically, the idea is that I'm hoping for a long stretch without mistakes. We know that there is one if the algorithm is mistake bound. And I want to use the hypothesis that is at the end of this stretch. Now, this by itself is better than using a hypothesis that is at the end of a short stretch, but it's not statistically robust enough. So what we're going to do is we're going to do an average. So average perceptron is going to return a weighted average of a number of earlier hypotheses, E here, where the weights are a function of the length of the stretch. So let me just write down the algorithm explicitly, and then we'll see. So here is how I'm going to train. And this is my notation here. M is the number of examples. K is the number of mistakes, which is also going to be the number of hypotheses we're going to have, because whenever we make a mistake, we change the hypothesis, right? So it's the same number. And CI is going to be my consistency counter. For every hypothesis, VI, I'm going to have a consistency counter that says how many examples I've seen without having to change this hypothesis. So with this, the algorithm is really very simple. So I'm initializing K to 0, V to 0, C to 0. And let's say I'm running over the data T times. For each example, I'm computing the prediction, dot product of VK and XI. If I'm correct, I'm not going to change the model. I'm just increasing my consistency count. Right? If I'm incorrect, I'm updating the model. VK plus 1 is VK plus the perceptron update rule. And I'm starting a consistency count from the beginning for the K plus 1 model. Okay? The output of this is going to be a list of perceptrons, V1 up to VK. Each one of them is going to come with a consistency count, how many times it survived without changing it. And then my prediction is going to be just to average this. So I'm giving this list. And given an example X, what I'm going to do is I'm going to predict with the ith model, weight by CI, and then take the sign of this average. Question? There was a question there. Yeah. Right, so I gave there two representations of the algorithm. One of them, the general one, and the other one is the case for the Boolean weight vectors. If the weight vectors are Boolean, then, okay, I should have said R here rather than 1. I'm adding a fixed number only for those coordinates that are on. And I'm adding nothing to those coordinates that are off.
Are
Yeah, so I should have said R here rather than 1, yeah. I'm kind of assuming in this box that R is 1, and here I'm assuming that, that it's 2. Yeah, you're right, it should be R. But it's a constant, and it's only added to those dimensions where the features are on. I cannot say it. I agree. I don't know whether the hypothesis that was good for 1,000 examples is going to be good on the next example. No idea. Moreover, I don't even have a way to say something about the probability of it being good. At least so far I don't, because we haven't developed tools for doing it. But what I'm waving my hands around is just a claim that intuitively, if you have two hypotheses, one of them was good for a lot of examples sampled from your distribution, and one wasn't, then you would choose this one. And we'll quantify it a little bit later. At this point, I'm just giving you this as some kind of a intuition, and I'm using it to develop an algorithm that is better than the basic perceptron. Yeah.
So I thought perceptron.
Okay, so if the data is linearly separable, there's no problem at all. It will find a separator. If the data is not linearly separable, then you still want to use the final hypothesis or a hypothesis somehow, and then the question that I raised comes up. So in general, you will not see a lot of data that is linearly separable. So we want to deal with the general case. And even in the case of linear separability, as we said, perceptron finds one linear separator. There are infinitely many linear separators for the data, and there could be a question, which of them do I want? Okay, yeah?
But if you consider the distance square error,
Yes, but again, the question is going to be, so now the question is about a different algorithm, an LMS algorithm, not about perceptron. LMS algorithm is guaranteed to find the minimum with respect to this data set. Is this what we really want? So it's actually a very important question. I'm going to get to it a little bit later today, but let's just clarify this issue. So if we choose LMS as our loss function, we are minimizing this loss function. And we can get to the real minimum relative to this data set that we have with gradient descent. This is not really what you want. What you really want is to minimize the number of mistakes you're making. These two are two different things. Is it clear that these two are different things? Minimizing the LMS loss and minimizing the number of mistakes on the same data are not the same thing. Hopefully they are related enough so that if I minimize LMS, I'm okay. But it's not the same thing. Let's take a picture here. Okay, here is a picture. Let's take this point and move it to the roof of the building. It's going to impact LMS a lot. Or we can move it to the other side, actually, to the floor. It's going to impact LMS a lot, right? And maybe it will cause all the line to move in that direction because the error that is incurred by this specific point is huge. And if I just move it maybe here, the line, all these are going to give me small contribution to the LMS, not as large as this point that I moved. That's not what we want. We really want to minimize the purple points that go to the red side, the number of purple points that go to the red side, plus the number of red points that go to the purple side. Okay? These are two different things. Yeah.
So for V in the algorithm,
Okay. So one of the nice things about perceptron is that the answer is no. You actually don't need to. Now, there are going to be there are other algorithms where these normalizations things are actually important. It turns out that for perceptron, you don't need to normalize. It's a very simple algorithm to run. You don't need to do it. So this is really a real algorithm that is going to perform as well as any other algorithm you need to run. So let me move a little bit forward, and I think some of the issues that you're asking about now are going to come up in the next few slides. So so I want to suggest another modification, again, a modification that is really important, and this is another regularization type. So we talked about the need to find a separator. And let's take as an example the linearly separable case where we are going to find a separator here. It could be that the line that we'll find, it could be this dotted line here. It's separating the data, but it's actually touching a red point or almost touching a red point. The other dotted line has the same property. It separates the data, well, almost separates the data, but touches a point. What you want is you want to find something that is basically in the middle as much as you can. And the way to achieve it is to think about trying not to fit a linear separator, but rather a thick linear separator. There are several ways of doing it, and we're going to see this a little bit later, but this is somewhat of a hack that actually performs very well. And the hack says, you know what? I'm not going to promote the weights when Wx minus theta is positive, but rather when it's greater than some fixed number here. And I'm going to demote same condition, not when it's less than 0, but rather than it's less than something. So I'm kind of forcing a thick separator here. Now, the reason I'm calling this a hack is because you can see that this gamma here is not a real margin. It's what we call a functional margin. As W goes throughout the algorithm and grows, the role of this gamma is going to diminish with time. Nevertheless, because you started well, it turns out that this is a very important and useful addition to the algorithm. By the way, the two things that I talked about before, I called it average perceptron. You can do the same thing with Wino. This trick, you can do the same thing with Wino. So these are general tricks. Here is one other extension that I want to mention, just because I knew that the question that came up earlier would come up. So here is the question. So this is my linear separator. That is this black line here. This is the normal. So this is W. And this is a negative example. Now, I have to, it's on the positive side, so I have to change something. I'm going to change this way. And the question is it guaranteed that after I change, this purple example will be predicted correctly? And hopefully, I kind of convince you that the answer is no. What's going to happen is that this line may move a little bit closer to it, but perhaps not enough so that it will move to the other side of it. Right? Now, I could, the size of this step depends on R. So what I could do is I could choose R adaptively so that I guarantee that this last example I will not make a mistake on anymore. And if you do the algebra a little bit, you will see that this is how you want to change it. I'm not going to do the algebra, but you do it. Basically, this just amounts to doing the following thing. You take this example, you predict on it, you see a mistake, you update. You predict again on this example. If you don't make a mistake, you're happy and you continue. If you do make a mistake, you update again. And you can update on the same examples as many times you need until this specific example is not predicted mistakenly anymore. So basically, this formula is essentially doing that. It's compiling all this prediction on the same thing. And again, this is an extension that you can suggest to perceptron or to Winnow. Okay, so there's a lot of other changes, bells and whistles, that you need to add to an algorithm. So I'm mentioning here a good implementation that was developed here. It's called SNOW for sparse network of Winnows. That has to do with the architecture of this classifier. Essentially, it implements several linear classifiers, versions of Winnow, perceptron, and naive Bayes that we'll get to a little bit later. And it has all the bells and whistles that you need in order to actually run it in real applications, form regularization, conversions to probability, has sort of capabilities for automatic parameter tuning, which is very important in real life, multi-class classification, pruning, various other things. And this is also the version that is implemented in LB Java, which is another program that we have. You can go to this page and see these programs there. So as I said, there's other extension that in practice you really need to do. Okay, so I talked about extension mostly in the context of perceptron, even though, as I said, all these extensions apply also to Winnow. I want to talk about one important extension for Winnow. I wanted to talk about the algorithm for reasons that you'll see hopefully later today. I already mentioned that, or we proved, in fact, that it has some nice properties in terms of dealing with sparsity. But in order to prove it, I simplified the algorithm a lot. And I want to talk a little bit about how to actually make it more realistic. And the one important thing that you probably noticed is that this algorithm only learns monotone functions. What do I mean by a monotone function? Any suggestion? Okay, so if you think about it in terms of Boolean functions, disjunction, conjunctions, other versions of Boolean function, it means no negations of variables. You've seen the notion of monotone functions in some other classes. Calculus, real variables, what was it there?
It's either decreasing, staying the same.
Monotonically increasing means when x grows, y also grows. It's the same notion here, right? So you can say monotone function, you can take the Boolean definition that you said, no negations, but if you think about it, it's identical to the notion that you talked about when you learned real valued function, real analysis, whatever class you've taken. If x grows, which means in the Boolean case would be you take an x, and if it's already 1, there's no place for it to grow. If the feature is 0, you change it to 1. In this case, the function also grows. So if it was 0, it either stays 0 or goes to 1. If it was 1, it will stay 1. The same notion. So why is it the case that Winnow learns only monotone functions? Why is that? How do you see that from the way we learned and expressed the function that this will happen? The weights are only positive, right? We started with 1, 1, 1, 1, 1. and we only doubling or dividing or multiplying by something, dividing by something, the weights are going to be positive. It will not be able to do anything with negations, right? So what do we do? If I want to learn general Boolean function or general linear functions, what do I do to get around the fact that all my weights are positive? Yeah? Right, so that's the standard solution. So what I will do is I will take, okay, I have a vector x. I'm going to put another x next to it with all variable negated. Now, if I use the same algorithm with positive weights, I'm actually learning a general function. N weights are positive for the positive weights. N weights are positive for the negative variables. So I'm learning a general function. So that's the standard solution. All I did is I'm learning 2n variables instead of n, not a big deal. All the bounds that you can prove about we know, instead of n will become 2n, not a big deal. The key thing that we proved was that it was k log n. Now it will be k log 2n, not a big deal. Hopefully you agree with me. So that's a solution. But sometimes it's not a good solution. Can you imagine a downside for this? I'll give you the scenario. So we talked about the fact, when do we care about this k log n thing? Sparse case. Let's take the sparse case in the data domain. Let's assume that you have 1 million variables, but in a typical example, only 50 of them or so are on. So you have 50 ones, and the rest of the million are zeros. What's going to happen with the duplication trick? How many are going to be on now? Almost, yeah. 1 million exactly, right? Because in the left part, there are going to be 50 that are on. In the right part, 1 million minus 50 are going to be on. So it's okay. We can run the algorithm. Everything is going to be fine. But we're going to carry very dense examples now. And implementation-wise, it's not a good idea. You don't want to do this because we do realize that the sparse case is the interesting case in many applications. So we're going to do another trick, and it's called, we're going to change the algorithm a little bit. What we're going to do is we're going to keep 2 weight vectors, essentially 2 weights for each variable. And the effective weight is going to be the difference between them. So this is the algorithm now. So we have 2 weight vectors. I call one W plus and the other one W minus. And I keep the same X as I had before. If the example is positive, but I made a mistake, that is, this is my new feature vector, the difference between W plus and W minus. Dot product with X is below my threshold, then promote W plus, and at the same time, demote W minus. Of course, do it only for those features that are on. I'm thinking about the Boolean example now. And same thing, if the example is negative, and I predicted positive, then I'm demoting W plus and promoting W minus. And it turns out that this algorithm is having all the nice property that Wino has, but it's much better to use. In fact, it turns out, and it took about 15, 20 years maybe to prove that you can generalize this algorithm to the multi-class case. This is a Boolean case, right? We have positive example, a negative example, and it has very nice properties that people were looking for but didn't know how to achieve. We're going to talk about it a little bit when we talk about multi-class. But it turns out that, the solution to this problem, the multi-class problem, was already here, only that people didn't realize that the only thing it takes is to generalize this simple algorithm to k outputs. Okay, so one other extension of Wino that I want to quickly go through. So again, you can provide a lot of properties for a lot of learning algorithms. So I want to highlight one important issue, robustness to noise. You can say, again, a lot of things about noise. And noise is important because in realistic situation, the data is going to be noisy. You can think about a lot of different types of noise. What I call here classification noise is the case where the label is wrong. You look at an example, someone told you it's positive, but actually it's negative. Attribute noise is the noise where you look at an example, x7 is 1, actually it's a measurement error, x7 is 0. Okay? And you can think about other types of noise, which I call here adaptation. Let's say the target function changes with time. Let's take the simple case. Just to illustrate it, we learn disjunctions, but there is an adversary or nature that, from time to time, they drop or add a variable from the disjunction and keep on producing examples for you. Now they are labeled based on the new disjunction. Of course, you'll have to keep learning and adapt your data, your hypothesis. Right? And this is, again, a realistic situation. It's kind of like the case where you train on one data set, but when you test, you see a somewhat different data set, taken from a somewhat different distribution. All these are very related problems, so it's the adaptation problem. So I'm going to show a very simple algorithm that will give good intuition for and good insight to how to deal with adaptations and how not to deal with adaptations. So here's the model that I'm going to use. I'm going to, as I said, I'm going to assume disjunction. And we will have an adversary that will change the target on us as we learn. This is kind of the scenario. So we're going to, so the adversary may change the target concept by adding or removing some variables from the disjunction. And of course, there has to be some cost to it, because I cannot expect that I will learn the disjunction now, the moving disjunction, with the same mistake bound, say, as I did before. It's a harder problem. So I want to quantify how much this moving target is going to add. And the way I'm going to quantify it is I'm going to say the cost of each addition of a variable is 1. So now quantify my performance also in terms of this cost. I'm not going to cost anything for removing this junction because that just makes it easier. So let's just cost the algorithm 1 when a new variable is added. So the learner is making prediction on the examples using the current hypothesis. Then they are being told the correct answer, just the standard model. And what I'm going to do is I'm going to change the Wino algorithm in the following simple way. The only thing I'm going to do is I'm going to run Wino, only that I will not let weights to go below a half. Once they get to a half, I'm not demoting variables anymore. Okay? So you see that in Wino in general, I either double the weight or divide the weight by 2. Here, what I'm going to do, I'm still going to double when needed. But when I'm dividing, I'm first going to look at the weight and say, is it already a half or below a half? In this case, no demotion. Just keep it as is. What is the intuition here? Or let's wait with the intuition. So my claim is that this version of the algorithm is going to make C log n mistake, where C is the number of added variables by the adversary. So one thing you can see here is that really generalizes what we did last time. imagine that last time we started with an empty disjunction, and the adversary adds up to k variable with time. Then it will be k log n. So it's a generalization of the previous algorithm. And the analysis is really the same. So last time we split it into two cases. U, mistakes on positive examples. V, mistakes on negative examples. And we analyzed U. Nothing changes in the analysis we gave for U, right? You promote, and you only promote on important variables. You never demote on important variables. So nothing changes. And the only thing that changes here is the analysis for the number of mistakes on negative examples. If you remember last time what we did, we looked at the total weight. We said that the total weight was n. And then we can do two things to this total weight. Either we double it, but when we double it, we add at most n. Why did we add at most n? Recollection, yeah?
But you're only going to double the weights that are...
And I made a mistake. I made a mistake, so it's less than n, and I'm doubling something that is less than n, so I'm adding at most n. And the same thing is going to happen now. When we demote, we said, well, you're dividing it by 2. What are you dividing by 2? You're dividing by 2 something that is greater than n because you made a mistake. Right? So it was greater than n, that's why you made a mistake, and you're dividing it now. So you're losing at least n over 2. Right? Now, if you think about it, we're losing at least n over 4. Because, think about what you have now. If all of them are already at the half, there's nothing you can do, right? But it's greater than n, so you're dividing those that are not greater than half. But those together can weigh no more than n over 2. And therefore, you're losing at least n over 4. Basically, it's the same algorithm and the same analysis, but the lesson is really important. I want to get to the lesson, which is the intuition that I asked for. Where is it? What is the idea now, if you think about it? Why did I bound it by half? I didn't want to let the weight go too fast to a very small number. Yeah? Exactly. So you want to be robust, and you can anticipate that some of the variables may come back. Right? Their adversary will suddenly decide that they're important. If you demote them too much, it's going to take you a lot of time to recover. If you bound it, you're going to recover much faster. And that's actually very, very important intuition in real-life adaptation situation when there are some learning policies, I'm going to hint on one in a few minutes, that like to eliminate weights because they say, you know, I want to eliminate weights because then my hypothesis is simpler. It has less non-zero weights. You're going to pay for it in an adaptation situation because if suddenly this variable becomes important, nothing you can do. So this is actually an important situation. Okay, so I want to kind of fold back what we've done in the last week or so and put it in a more general scenario, the scenario that you'll see in papers if you read the last 5 or 10 years papers, where kind of machine learning has been developed and people have seen a lot of connection between different things. So I want to put these connections in place now. And surprisingly, what we've done so far actually gives you the tools to understand this, I think they understand this kind of very general view. So what have we done so far? We talked about a general stochastic gradient algorithms, right? So we had a bunch of examples. I use Z to denote X, comma, Y, the example and the label. And we said that there is some risk function that we've written this way, the expectation over the data, X cross Y, of some Q, which we call the loss function. Now, really, we cannot minimize this. We're going to minimize the empirical risk, right, which is the average of Q on those examples that we've seen in the training. That's the basic thing that we want to do. Now, in stochastic gradient descent, we agreed that the way we're going to do it is by incrementally update the weight, step by step, and this is how we update the weight. The weight at time t plus 1 is the weight at time t minus some constant times the gradient of our loss function. Right? That's what we said. I'm denoting here by G. This is the gradient with respect to W of our loss function, which from now on I'm just going to call GT. The gradient at time t. So that's a general algorithm. And it turns out that, okay, I just want to remind you that we also talked about gradient descent, the batch algorithm, that does this over the sum. So every time it touches all the example, but now we're talking about the stochastic case or the online case. These two words in our context are interchangeable. So that's a general scheme. And then with this general scheme, we talked about LMS. Right? This is the first thing that we did in the class. We said, you know what, RQ, our loss function, is going to be this. It's going to be the difference between the truth, Y, and the prediction, WX. No sign. I'm not thresholding the prediction. I'm not saying if WX is greater than something, it's 1. If it's less than something, it's minus 1. I'm just taking the value as is. And we square this. When we differentiated it, this is the rule that we got. This is the LMS rule, and this is the SGD algorithm that you were asked about in the first part of the exercise. It's also called Widrow-Adaline. It was proposed in a different context, by the way, not machine learning, more controlled theory, also in about the same time, in the early 60s, I think, by Widrow. Okay, so that's one algorithm. Now, in the exercise, we asked you to think about a different loss function. The loss function that we ask you about is this, is hinge loss. In hinge loss, you have a different loss function. It looks like this. So if the LMS is this green thing, quadratic function, the LMS is this blue thing. So if you are correct, it's flat here. And if you're incorrect, your loss goes linearly with WX, with the dot product WX. Right? This is what happens with this function. Hopefully you had time to think about it, and then you're convinced that this is what's happening. Now, if you now use this, and you use this stochastic gradient descent principle, you get this algorithm. You get an algorithm that says, if you make no mistake, don't update, because it's flat here. If you make a mistake, then update by adding R, learning rate, Y, xt, which is an algorithm that we called perceptron. So basically what we get is an algorithm that you know, that in fact was invented completely irrespective of this theory of gradient descent, was invented directly, but turns out that you can put it in a general setting. Okay, with this general setting, you can do more things. You can invent other algorithms, and you can change two things. You can change loss functions, or you can change other tricks in the algorithms. And one of the issues that turns out to be very important is learning rate. In practice, even though I didn't say it, when I wrote it here, I put RT, but all the algorithms that we talked about so far, R was a fixed number, did not care about T. In practice, you want to change it. Moreover, I want to remind you here, this is just a technical thing that you know, that we're talking here about vectors, right? You actually do a change for each coordinate separately, right? So really, you have to write it as WT feature J and gradient T feature J, right? For each feature in your feature vector, there is a gradient and there is a weight update. Agreed? That's important because you're going to implement it in the problem set, so you have to realize that we're talking about vectors here. Okay. And as I said, we can change the fixed. So AdaGrad is a new algorithm, relatively new, the last 3-4 years, that actually decides or suggests to update, to adapt the learning rate using a policy that looks at previous gradients. Basically, the idea is that if you have features for which you make a lot of changes, you want them, you don't want to take them so seriously as for features that were constant and suddenly there is a change. You have to listen to this change. Maybe it's important. That's kind of the intuition. And the way to accomplish this intuition, we do it this way. So we're going to say that a per feature learning rate is going to be this. So at time t, this should be j here. The jth feature is going to be changed this way. R, which is a constant, it really doesn't, not so important, divided by GTJ square, where this capital G is the sum of squares of all the gradients that we've experienced so far for this feature. So you can see that if so far you did no change for this feature, right, so this is 0, basically nothing is going to happen. You'll just have R here. But if, on the other hand, you've made a lot of changes for this feature, then the denominator is going to grow, and the change that you're going to make is going to be smaller. So it adapts to how many changes you're making in this change. And the idea is, the hope is, that this is supposed to be a better way, sort of somewhere perhaps between perceptron and Winnow in terms of changing weights, but it's going to be adaptive to specific features. So hopefully you will play with it in the next problem set, and we'll see what's between Winnow, perceptron, and this algorithm in terms of adaptation. Okay. You know what? I'm going to start with this next time, and I'm going to say have a good weekend. And don't remember to start working on the problem set. Yeah.
So in training the examiners, when using that recording the number of